Okay. You don't need to see my face. All right, just want to make sure everyone's seeing my slide correctly and sharing the correct thing.
Yes. Yeah.
Okay, sounds
That's
good.
good.
Alrighty, so once again, thanks everyone for coming. Today, I'm going to talk about calibration, artifacts, and quantification for electron ptychography, because I feel like I have been giving 2 talks at NMM, and I don't want this study group talk to become a replay of my NMM talk, even though I'm sure we'll still have a lot of interesting discussions here. But today, I want to touch on something more practical, because now we have, fortunately, we see that the ptychography community has been greater and greater in sizes, and a lot of interesting work has been popping out very soon. But I think there are a lot of these like fundamental stuff, or maybe the dry stuff that doesn't directly get into a paper, need quite some attention. So today I'm going to touch on these topics, which can appear to be a bit dry, but I hope people will at least still learn a little bit from it. So there are many available ptychography packages right now, and you can, that's pretty much the first thing you will want to kind of like make a decision here, because most people don't have the right to choose what microscope to use or what detector to use, but at least you get to choose what ptychography package you're using. And pretty much there are 2 mainstream ptychography approaches. One is the direct ptychography that you can be doing some single sideband or WDD method. They are some variants similar to ptychography, but also like 4D STEM approach, kind of like tilt-corrected bright field, or people call it parallax. You can get something very fast from the 4D STEM data, or you can do some machine learning approaches to kind of get like a, I should be adding Rahim's stuff here. And you can do some machine learning stuff to get very fast result. But nowadays, most of the result or the papers are published other than these direct ptychography, which is very good for low dose or beam sensitive materials. Another mainstream is actually the iterative ptychography approach that you can see that there are more than decades of development in terms of our packages, especially starting 20, I think Tycho shows come out around like 2020, but even before that, there are like a very long line of effort in terms of making iterative ptychography packages, like all these like famous algorithms like ePy and other stuff. And especially starting this year, I believe me and Colin at MIT and Devanshu, we are all start making these new iterative ptychography packages using automated differentiation. And even before that, we have Dr. Mingdu at Argonne has already been using this AD in especially X-ray ptychography. And now this year they have a newer version, not newer version. They have a Python. They have Tai Chi coming out basically, and it's going to be introduced again in this study group later as well. But then I want to talk about mostly about iterative ptychography algorithm and packages. They give us high quality result, but there are a lot of subtlety in these high quality results, and we're gonna specifically talk about these. And so the good thing about iterative ptychography algorithm, I'm sure most people are already aware that it allows us to do a lot of these fancy things that you cannot do with direct ptychography. For example, you can easily handle partial coherence and other experimental errors using mixed probe modes. And also you can easily do this multi-slice reconstruction that allows you to get that sectioning with a single 4D SEM pattern without requiring any tilt or tomography setup. And also it allows you to do easy position correction. So all these sounds great. That means with iterative ptychography, you just take data and the algorithm will sort of correct things for you. But things don't usually go that smoothly, as these things, once you start building your model more and more complicated, there's always this risk that you may be overfitting your result, because ptychography, in essence, is the inverse problem-solving technique. And once you start adding more and more degree of freedom, there's a saying that once you start adding more and more degree of freedom, you'll be able to fit anything from your data. So once you start fitting your data by having an ultra complicated model, then the interpretability of your model becomes less and less, which is a huge problem for scientific discovery, because if you have a model that just fit perfectly to your data and you just can't explain what that model means, then that's pretty much the same dilemma of what we are having nowadays for the machine learning era, that we have all these very capable models, but we don't actually know how they work. And from engineering or business purpose, that might be okay. But for scientific discovery, we do care how do we get those answers and how reliable those answers are. So that will sort of be the main topic for today. And common challenges in ptychography, which will perfectly be the three topics I'm going to touch on, will be calibration, artifacts, and quantification. And we'll spend most of the time in calibration, and maybe another 50% of the time we'll be touching on artifacts and quantification. I'll keep things more or less on a high level because it will take too long to go to every bit of details. So let's start. First start from calibration. There are many things in ptychography requires calibration, and a lot of them are not restricted to ptychography. It's actually very general to the entire electron microscopy work. If you want to do high quality microscopy work, this calibration really matters. And from a ptychography point of view, calibration really changes how the convergence goes and how fast you can converge to a result. So most of these iterative ptychography approach, you can think of them as like a gradient descent approach, that by starting from a different initial guesses, which is determined by your calibration, you can sometimes converge much faster, sometimes you converge much slower, depends on where you are. Sometimes you may just get stuck, you never get to the real result, and sometimes it will just fail on you. So here are the important factors for the calibration. Some of them might seem very trivial. For example, KV, you'll be like, why do I need to worry about KV? But I can tell some people in the institution, if you have an EOS installed on your microscope, you may see that someone like your previous user might just like change the KV by having a prism, so that it doesn't need to shit as much of the KV on the prism part. So the EOS software can actually change your KV when you acquire the data. So that's just one example. And another couple small example, like whether you center your diffraction pattern on your detector, or whether you have the elliptical distortion in your diffraction pattern or the background. So all these like tiny things, they will start building up. But I'm gonna talk a little bit more on these, the most critical part in terms about calibration. Okay, very first thing, the k-space sampling. So when you acquire a 40-cent data set, there are two sampling steps you need to be very careful. One is the k-space sampling. In here, I mean the k-space pixel size on your detector, which means each pixel on your detector, we need to assign it a physical unit on it. And usually, a lot of people will be doing a convergence angle, but here, fundamentally, these k-space sampling means that if you have a diffraction pattern here with n pixel, and each of the pixels correspond to a angular spread or a like an inverse Armstrong or a wave number here. And these are the spatial frequency. And the simple formula to remember here is this is related by Fourier transform. So there's no computation weirdness here. So your real space pixel size, which define your object and your probe in real space, is equivalent to 1 over k range in units of 1 over Armstrong. And this k range means the entire bandwidth of your diffraction pattern, which means that if you think about this center part as a 0 frequency to the edge of the diffraction pattern, that is essentially the Nyquist frequency of your diffraction pattern. Here, usually we call it as a maximum collection angle. And most of the time, we control this with our camera lens on the microscope. But since the camera lens calibration doesn't necessarily need to be accurate, it's not really transferable to other institutions. So I would highly recommend people just communicate using the inverse Armstrong, which actually means something physically and transferable. And a common number to remember is if you have a Kmax, which is your maximum collection angle 2.5 inverse Armstrong, that typically means your real space pixel size is around 0.2 Armstrong. So when people come to me and ask what would be a good collection angle for your Tycho data set, I usually would say this is a good number, 2.5 inverse Armstrong for your collection angle. And for multiple reasons, one is they give you enough sampling, and second is your spatial resolution, especially the lateral one, is also determined by this Kmax, given that you have enough signal-noise ratio. If you have a very low dose data set, even you acquire up to high collection angle, there's just no signal at all, then you don't actually get those spatial resolution. But given enough signal-noise ratio, this Kmax here, or the maximum collection angle, actually determines your lateral spatial resolution and, of course, your real space pixel size. So why is it, how does this relate to calibration? So a lot of people, including me, we start using Ptychography with a fantastic full-slice variant coming out from Ptychography developed by Yi. I mean, the full-size variant. And people are using this very common number called radius of bright field, or RBF. And the reason they use it to calibrate their diffraction pattern is because that's a very easy number to get from the user interface of your microscope. But the problem is this RBF has a couple issues. One is the convergence angle on your microscope doesn't necessarily need to be calibrated. Depends on how well the alignment was done. It can be off by somewhere between 2 to 5 to even 10% is possible. And another problem for this RBF value is given a vacuum probe or the diffraction pattern acquired at a vacuum region, how do you actually measure the radius of this thing? Because they are point spread function of the detector. When the electron hit on it, they actually spread out a little bit. And once you measure something like this, do we do the full width half max? Do we do the full width 90th max? Do we do the full width 100th, not 100, like 1,000th max? Something like that. So that makes things very challenging. And we do have a quite nice discussion about whether this is a good way to do calibration, or how do we actually put a scale bar on our typographic reconstruction on the Tyred GitHub issue number 17. And if you're interested, feel free to check it out. But here I want to argue that if you want to calibrate your DK, instead of fiddling with your convergence angle calibration, which most people are probably not allowed to do in their institution, you should probably be thinking about keeping your own set of calibration by doing a nanobeam electron diffraction, which allows you to directly calculate DK with a known crystal, of course. Ideally, this crystal is strain-free. You can actually get a very nice calibration sample from companies. But first, you get these known crystal, and then you move your you change your microscope operation mode into the nanobeam electron diffraction, which basically it will change your probe forming optics, just a convergence angle, but it will keep the projection system unchanged, which is the one that actually controls the camera length. So in this case, once you change your convergence angle to a smaller value, I think the smallest one that you can achieve given a nanoprobe mode is probably a few millirad to maybe hundreds of a microradian. But that's usually good enough for us to measure a couple of black spots here to get a good calibration of your DK. And if you do this with a known crystal with different camera length, ideally you'll be able to form a calibration table here, which will very likely to be KB dependent. And with a couple aperture, you'll be able to get the nominal. So this is the convergence angle you will usually get from your user interface. And here's a calibrated one. And I can say we are doing a pretty good job at 300 kV calibration back in UIUC during my PhD. But the 80 kV one doesn't look that great, and we're having somewhere between 5 to 10% of error. But just saying, if you do this case-based calibration with a known crystal, you can actually form this shared calibration table at the group or institution level instead of everyone optimizing their Tycho reconstruction convergence angle and DK for each data set. I've seen people using Bayesian optimization to optimize their convergence angle for each data set, even though they're all using the same aperture, which makes things very confusing and much harder to reproduce things. So I'm highly recommending people to start using these nanobeam electron diffraction technique to actually calculate your DK per camera length and per convergence angle for each KB. And another common thing for calibration is the scan step size here, that most people ideally would have a scan generator for their normal ADF stem and also for their 4D stem detector. And here I just want to touch on this, that these 4D stem scan generator, they may have different scan step size, or in other words, magnification or field of view with your common ADF. detector or a scan generator, it's very common to see a difference in the field of view by like 3 to 5%. If you have a bad calibration, it could be up to 10%. And of course, I would also recommend people to do this using just a known crystal, and you can actually do this with a virtual image. You can measure the lattice constant in real space or in reciprocal space. But again, most of the time these 4D SEM detectors are fairly slow. So if you want to do this calibration, you want to make sure you have inserted the holder for long enough so it's now stable. And also you want to start from a strain-free crystal. But this one, comparing to DK calibration, the scan step size calibration doesn't need to be that accurate because you will always get some scan distortion from sample drift. This is just inevitable unless we have a total new innovation in the holder stage in the microscope. But like I said, because you always have these like sample drift, so maybe the best you can do for your scan step size is an error bar around like 1% or so, but that's still better than 3 to 5 or even 10% of this. So you do want to calibrate your scan step size, and ideally you make it into a table as well. And when we talk about these like simple drift, there's actually a couple more factors that usually come into play. And like I said, you don't necessarily need to calibrate your scan step size down to like 0.5 or 0.1%, like by having your holder sitting for 24 hours or something like that. And because when in practice, you always have these scan distortion. And I personally think it's probably easier to just handle a scan step size as a rough calibration, 1%, 2%, probably okay. And you treat all the data set dependent scan distortion into the scan affine transformation here. And you can see that there are actually 4 values we are using to define the scan affine transformation, including the global scaling, and rotation, asymmetry, and also shearing, which is just essentially a 2x2 matrix. And by having this scan affine transformation, you'll be able to correct your the scan distortion in your 4D SEM dataset even before you run your typographic reconstruction. And there are quite some work before that's touched on how do you actually get the scan distortion corrected on your 4D SEM dataset. I'm going to talk a little bit more later on that. But here, just to give you an idea that you roughly calibrate your scan set size, but eventually you will want to have the full 2x2 scan affine transformation matrix to be pre-calculated if possible, so that your typo reconstruction will be converging much faster and also to give you a more accurate result afterhand. Okay, so here's just an example of a typical raster scan pattern that you can see that this is acquired back in my PhD MPAD-1, that we have a 1 millisecond dwell, but also 0.86 second of readout time. So overall, each diffraction pattern is separated by nearly 2 milliseconds, which is very slow. And given that we have a drift rate of around things like 0.1 angstrom per second, and we're taking only 128 by 128 diffraction patterns here, you can see that there's a significant amount of shearing happening along the slow scan, or between the slow scan and fast scan direction. And like I mentioned, there are a good line of research, mostly coming from Professor Shou-Sung Ning right now, talking about how do you actually correct or to calibrate to find these scan affine transformation matrix from these prior work. And also, if it's just like, for example, like a global scan rotation that I didn't get to mention previously, but some of the microscope would have their scan generator or detector mounted with a scan rotation in between, and you will have to correct that when you run typographic reconstruction. And these numbers can be somehow tricky to get, and there's a very handy feature in Py4D SEM that allows you to sort of determine the relative scan rotation if you have a density sample 4D SEM dataset in real space. But just saying, here are the good references. You should definitely check it out. Currently, I haven't implemented these features in Tyra, but I'm very interested in doing that because that will literally save the users quite a bit of time of figuring out all these annoying scan distortion. But yeah, so this is very typical unless you have the high-end 40-SEM detector that allows you to run maybe like tens of microsecond per different frame. Otherwise, you should always keep in mind that your scan positions are just not square, and you do need to correct them for a accurate Tycho reconstruction. And since we touched on the scan rotation between the detector, there's actually one critical factor. A lot of people find it very challenging is to actually figure out the data orientation. And the reason for that is because, first of all, we have the optics in the microscope. You have a couple crossover. You have the engineer installed your MPAD detector in different angles. In UIUC, we have two MPAD. They are installed with 90-degree rotation. So similar things could happen to you as well. I believe most people with their MPAD detector, not even MPAD, with their 40-SEM detector, they might have a weird orientation flipping between the readout data and the GUI that they saw when they acquired the data set. And even after you acquire the data, when you load your data with different packages or with different libraries, or just display them with different software, you actually see a different diffraction pattern orientation, which is extremely confusing. And when you run Tycho reconstruction with the incorrect orientation of your diffraction pattern, you're actually going to see a lot of interesting stuff. So first of all, these errors are sometimes they can be very subtle. So this 100 means that I'm flipping only up down. And if you change the orientation of your diffraction pattern, you do get something with the same sort of the crystal structure. However, the contrast is totally wrong. And if you have a 180-degree of rotation, in this case, is you flip your diffraction pattern upside down and then left to right, then you are actually going to get an inverted reconstruction, which is these two are totally, I think they're mathematically equivalent to each other, except that your face is moving. Instead of having a positive phase shift, you're getting a negative phase shift. So the message here is the data orientation is very critical. You do need to make it correct when you have the 40-SEM data acquired and trying to reconstruct it. And it seems to be the very first barrier for a lot of users. So I actually I built this small plugin into Py40 GUI, which is a fantastic visualization software maintained and developed by Dr. Siebert Zeltman, currently at Cornell, but previously at Berkeley. And I just made this plugin so that you can actually check your data orientation in Py40 GUI, which has already checked that if you have your data orientation correctly set up in the Py40 GUI, you'll be able to just use the exact same flips in Tyred so they can get the reconstruction running. And if you go check out our Tyred YouTube channel, I actually made a 13-minute video talking about how do you actually find the orientation by checking the feature in your rungram, how they move along with your scan pattern. So just check it out if you're interested for more details. But getting the orientation correct is literally the very first step to get your Tycho reconstruction. Okay, so I'm gonna touch on a little bit on the defocus, and a lot of people might have experience of, okay, now I acquire a data set on the microscope, and it says defocus 10 nanometer. When I try to run reconstruction, it never works. It will always converge to some other probe. And the fundamental reason to that is because this specific number in your microscope user interface, first of all, it may not be 0 correctly because there's a button you can click called reset defocus. So if there's like a previous stored value, then this display value is just not going to be the actual value. And then even you reset your defocus correctly, such that 0 focus actually means at focus. When you change it to, let's say, 10 nanometer, then your actual defocus may not be 10 nanometer just because this value is actually not calibrated that carefully. And for again, for our own microscope at UIUC, for one of the KV, we actually have a 40% off of the defocus. I'm going to show you some data later. But basically, You will see a defocus value here, and if you lucky enough to have a probe corrector from the CS company, then you will also get the aberration corrector software. It's called Dcore here, that will actually also pump out a defocus value named as C1 here. Or if you're using a thermal fission microscope, they come with this very handy automatic aberration correction software called Sherpa that will also allow you to output some C1A1 defocus and fixed values. And there are all these displays defocus value. You may be wondering which one should I be using and how to actually get the correct defocus value for my Tycho reconstruction, because like I said, the initial value matters a lot for your reconstruction. And just a quick note here, Thermo Fisher defines the defocus here, the value shown here, as positive C1, which is the total opposite for most of the EM literature and software. That if you do APTEN or if you do Tycho Show full slice Tyrad, we all define our defocus as negative C1. So that in this case, overfocusing on the microscope will show a positive value, while overfocusing will actually mean a negative value in most of the other tychography software. And I believe most software will kind of like mention their convention somewhere, but it's just something to keep in mind that you might have a different sign of your defocus given where you get that number from. So like I mentioned, there's a 40% of scaling factor between the user interface defocus to the actual defocus. So you may wonder, how do I actually get this value? And the answer is surprisingly simple. So the steps are essentially, first you bring your sample at focus using piezo, and then you reset the displayed user interface focus to 0. And you want to make sure that the aberration correction software, they all show a very small defocus. So in this point, essentially, you're aligning their 0 baselines. And after that, once all the aberrations are aligned here, you can just turn your objective lens knob to change your focus to, for example, 20, -20, 50, -50. You change that, and then you just correct it with your aberration corrector software to see, based on the retrieved optics value from the microscope, what are the defocus value that the aberration correction software thinks that you're actually having. So by doing this, and you will actually be forming a very nice straight line showing, yes, we do have a scaling factor between the displayed defocus value from your user interface to the actual defocus value based on the optics. And just to keep in mind that this defocus scaling factor is very likely to be KV dependent and, of course, alignment dependent as well, and sometimes even mode dependent. When, for example, when you change your camera length, there are some hysteresis happening, such that defocus also changes a little bit. So this is just to give you at least a better rough start. But for large defocus value, for example, if people do somewhere like 20, 40 nanometer, this scaling factor can be quite significant and impacting your Tycho reconstruction convergence speed. You just keep this in mind, and if you get a chance, do this calibration at your home institution. You may find something interesting. Okay, so that's pretty much it for the calibration part. It's fairly dry and takes quite some bit. And now I'm going to talk about another common challenge in tychography, which is artifacts that we don't talk about it as much, but is critically important for interpretable results. So yes, artifacts affect interpretability, and most Tycho paper right now, you will find that we don't talk as much about it because they don't look great. And sometimes, for example, one of these archive paper that I found, they're doing a Tycho reconstruction just to compare with their S-metrics method. You can see that the top row are the reciprocal space probe, and the bottom row is the real space probe. They have reconstructed with 6 probe modes, and it is very common for tychography packages. You will be seeing that, especially in iterative tychography, once you do the probe retrieval, you will actually see that other than the first probe mode nicely centered, you'll actually get all of these like spurious intensity at the corner or the edges of the probe window. This is fairly common, and it's mostly because of the phase instability inside the reciprocal probe, and because we don't actually require a smoothness or continuity in the reciprocal probe. So when you do this pixel-wise updates, occasionally you will start seeing the spatial frequency being spread out into all these corners, which will give you the similar diffraction pattern at the end. So that's why it's some sort of ambiguity. But this is just one very common example of the probe artifact. And actually, there are a lot more artifacts coming in. I'm going to touch on a couple of these. Some of them are package or constraint dependent. Some of them are more data set dependent. But the rule of thumb here is you want to pay very close attention to your reconstruction, not just your object, but also your probe and also your position. And I'm gonna just give you some example of where to look at and how we may possibly correct them if I happen to know the answer. So here comes the very first example. I'm just gonna give you a couple of seconds to look at all these three reconstruction. Cool. So they all seem fine. But as the title said, these are good objects with bad probes. And what I'm going to show you is I have to actually manipulate and mess up the reconstruction parameter quite a bit. But if you mess up your aberration, if you mess up your reconstruction parameter quite a bit, you actually see all these weird probes. So you can see these like real space probe being duplicated at all these random positions. And this one actually nicely showing you an example of object probe intermixing, that these probes are duplicated with object spatial frequencies, and you can see there's pretty much just a duplication. And just because translation in real space is just a phase shift in reciprocal space, so you actually get the exact same diffraction pattern, or at least very similar given the experimental parameter. So when people show you a good object after their Tycho reconstruction, maybe the natural follow-up question is like, hey, what does your probe look like? We don't show these probes that often nowadays, but I do hope Tyred implemented all these very excessive summary figures in hope of the whole community will start looking closer to their reconstruction and not just like give pretty objects, because even you have a pretty object, it can totally mean you still get a very nasty probe, and that has significant effect in the physical interpretability of your final reconstruction. So this is just one example that even have a very good probe, if you have a very good object, you may still getting a very terrible probe. And another example here is, like I mentioned, there are significant amount of object probe intermixing, especially for iterative ptychography approaches. This is very sensitive to the optical condition. And for a simulated data set, sometimes you will see this because you do have a very, very strong signal from your diffraction pattern. Sometimes you see something like this. This is one of the worst examples you can have for object probe intermixing. You can see that the real space probe actually picks up a lot of these crystal structure in your object. And one of the reasons for this is because, first of all, this is a simulated data without putting any noise or dose into the data set. So the signal is being too strong. And secondly is I intentionally start from an incorrect probe defocus value. So this data set is actually simulated at focus. But when we do the reconstruction, I intentionally change it to like something like a 10 nanometer over focus. And you can start seeing that if you start from a very off initial condition, you may end up getting a lot more artifact than you initially expected. So this is the one type of object probe intermixing. There are other types of object probe intermixing, especially in K-space, you will be seeing. But I don't think I have an example here for today. So another common artifact, which this one I believe most people have probably encountered, is a wraparound artifact in the Z dimension. So back in 2021, when we were doing multi-slice electron ptychography, we do need to apply this so-called missing wedge regularization, or the KZ or arctangent regularization. Essentially, it is clipping removing the KZ information in the object Fourier transform. And if you don't do that, you don't actually get a reconstruction done. So everything is very noisy. And if you start applying this KZ filter, you start getting something reasonable. But I just want to pay attention here. If you start this like a typical parameter that you do multi-layer regularization with a parameter equals to 1 in, for example, full slice, and if you try this on this twisted bilayer WSC2 data set, you actually see that the top layer and the bottom layer, they look pretty much the same. And fundamentally, that is because there's this wraparound behavior for Fourier transforming a finite signal. So the top layer and the bottom layer are actually coupled together because we are doing the inverse Fourier transform to get the final object back. So that is a reason why in Tyred we actually implemented a real space regularization so that the top layer and the bottom layer can now be nicely decoupled, as you can see. But this wraparound artifact is very common for most of the multi-slice electron ptychography reconstruction, unless you start doing these regularization in real space to get rid of these wraparound artifact. And for example, if you have a tilted crystal, this wraparound artifact will literally slap the bottom layer on top to your top layer, so to make some ghost images of your reconstruction. And this is one common example of an object artifact. And here comes another more subtle artifact. I'm trying to wrap up in 5 minutes so people can ask questions. Okay, so this is more of a subtle artifact that I just want you to squint. And it looks like a very nice reconstructed images, but there's one thing I'm not sure if you noticed it. So if you look closer over here, there's actually a faint ghost atom showing up. So if you just adjust the brightness here, you can kind of see that occasionally you can see these ghost atoms showing up at high symmetry point. I don't fully understand the reason of this, because if we change the regularization or the learning rate or increasing the number of promos carefully, then I don't necessarily see this. But at this moment, I'm suspecting that's because this data set itself is a focus probe data set, and we have a fairly large scan step size, so things are not constrained as well. But just something to keep in mind that sometimes you may be seeing some faint contrast at high symmetry point. You probably want to ask yourself again whether this is an actual atom or this is just an artifact coming from Tycho reconstruction, because of this like translation symmetry in your scan pattern can sometimes give you some weird results in the Tycho reconstruction. And another common object artifact is the donut atoms. Some people call them the crater artifacts, or the black hole in the images. And it typically happens when you have a heavy atom like bismuth, and this one I think is in the neodymium atoms from a data set kindly provided by LOPA. That you often see these black hole or donut artifacts in these heavy atom sites, and even on simulated data set as thin as like 2 nanometers. And most commonly, people would attribute this to a phase wraparound artifacts here, or phase wraparound behavior in the reconstruction. And in Tyred, we actually experimented quite a bit to see whether we can reproduce this in a consistent way. But now we find that if you reduce the slice thickness to a reasonable amount, like 5 angstrom or thinner, depends on the of your Z number, you can actually remove these quite consistently by running a few hundred iterations. And as you can see, this is just the depth sum of the reconstructed object throughout the iterations. And you can see that I'm just going to play this again. You start from all black holes or donut artifacts, and by running a few hundred iterations with some real space blurring, you get to see, oh, now we have corrected all the black holes. But this is just something to keep in mind, that if you have the heavy atoms and sometimes you see these bizarre artifacts, there are a couple references already touched on why we're possibly seeing this and how to cure this. But now it seems like it's being performing fairly stable in Tyred already. Okay. And here comes another artifact in your object that we don't typically talk as much. And here I call this artifact double cone artifacts, and that is because if you run the the twisted bilayer WSC2 data set with extensive vacuum, you're actually gonna see these. Did you see that how there's like a ring irradiating in, such a way in focus and irradiating out? I'm just gonna play this thing again. Yeah, so it looks almost like a kind of like how the 3D point spread function of your of a coherent imaging technique. And I'm sure I'm not the first one to seeing these. And if you just take a cross section of this reconstructed object, you actually see these. In the cross section, if you do a line profile here and just do a cross section, it actually looks like an X shape. Kind of looks like the DNA shape. So you have an X here, and geometrically it feels like a double cone here. And you can see that from this very nice paper back in 2023 from Scoffing, they actually already mentioned these sort of features you'll get from the weak phase approximated phase imaging with the depth sectioning. You can see that these like tails. You may want to just check out the original paper. The contrast is not that great on the PowerPoint. But basically, this artifact is similar to the missing wedge artifact in tomography, that we just have limited optical information in our diffraction pattern, especially for the convergence and collection angle. So you are seeing these edges. And once you start increasing the convergence and collection angle, this thing gets sharper and sharper, and these angles get wider and wider. And most of the time, you're seeing this very clearly because I'm using a 1 angstrom slice thickness. But for typical multi-slice ptychography with thicker sample, usually you'll only see this at the very top and bottom slice, which we usually discarded or padded with vacuum. But this is something to keep in mind that technically for each of the atom, the single atom you resolve, you actually see this X shape in the cross section. If you pull up the 2021 Zen's paper in multi-slice electron ptychography, and you look for the substitution atom that they resolve, you can actually see similar tails or the double cone artifact as well. And I think this is fundamentally limited by the optical condition. And here's the, I think this is maybe the last example or last two example of the object artifact. So here's a tie-rare reconstruction of the PSO dataset, and here's a reconstruction from another package that I just want to show you. Sometimes you get these rippling coming out from the atoms. It may be coming from the regularization they were using or some sort of settings that haven't really figured out. But if you take the Fourier transform of this object, you can see that the FFT for the tie-rare reconstruction shows a natural decay here because we are bandwidth limiting the spatial frequency up to a certain value. Because even though the FFT have a Kmax reaching around 9 picometer of the object, the actual data is only acquired up to a Kmax around 18.8 picometers. So somewhere half here because we are padding the diffraction pattern to get more pixels in real space. But here, with these rippling artifacts, you can actually see that you are getting information transfer so far way beyond the actual data you collected, which to some extent, that's just image artifacts. So don't get too excited when you see a very far information transfer, and I'm sure people would still try to report values using information transfer, but just something to keep in mind that information transfer itself is just not a good metric for spatial resolution, and there are all sorts of possible artifacts can make the number looks good. And lastly, just going to talk briefly about quantification. So, well, we should always try to do our type of reconstruction in a quantitative way, that you measure things, you measure the face value, you measure the structure. But before we get to any scientific conclusion, you need to think two things. One is whether our result has converged or not. So convergence is very important. And convergence means that your reconstruction doesn't change with increasing number of iterations. So that means it's converged. But even though your reconstruction is converged, doesn't necessarily mean it converged to the right result, which means the accuracy here. And two common metrics we want to monitor, which is, first of all, the proposition and object structure. That's important for people to do any sort of strand analysis, displacement analysis. And second of all is literally the retrieve value for your face, or your object face of your object. So there are quite some paper already, especially from Jim's group, touching on this topic about how quantitative we are in terms about the retrieve phase value. And I recommend people to definitely check out all these wonderful papers discussing on this. And we're also working on our own one as well to see whether different experimental conditions would change the retrieve phase value here. But the key point here is in order to make quantitative interpretation of your data, there are a lot of these subtleties you will want to keep in mind, especially after I talk about all these possible artifacts, and sometimes they can be quite subtle. So in terms about quantification, here I'm going to give you a quick example of the proposition correction, which everyone knows that it can be very slow. And here's just an example of the PSO data set that I have been already reconstructed for 50 iterations. Just gonna play it. You see that we reached a pretty decent reconstruction. Like in my demo prem file, I'm using only 200 iterations, but the whole structure is still constantly changing up to like a few thousand iterations. And it's more or less converged after maybe like 4,000 to 4,000 iterations. But I'm just gonna scroll this so you can see a little bit better. So maybe after like 2,000 iterations, the things are slowly being better converged. And like I said, in order to put the scale bar here, you need to know the dx number, the pixel size in real space, which is physically determined by the maximum collection angle of your diffraction pattern, which hopefully you have been calibrated. But in order to actually put a scale bar here, you do need to make sure that your object has your proposition and your object structure has correctly converged. And you may think, hey, if it will converge in a few thousand iterations, I'm just going to let it run, right? And a few thousand, fine. We have powerful computer, we can just run it. But beyond that, here's an example of the twisted bilayer data set that I intentionally put a 3-degree rotation in the incorrectly. And the message here is your proposition correction can still fail with a bad initial condition. So 3-degree, it doesn't sound too much. And typically when you align your scan pattern, most of the engineer do a pretty decent job, can put it around like 1 or 2 degrees. So 3 degrees is not too much. But for this specific data set, I'm going to show you how proposition correction can actually fail. So this is quite concerning because you see that most of the images are actually correct. So the biggest problem here is that the Tycho reconstructed image, you don't have a single binary true-false value whether this is correct and whether this is incorrect. The reconstructed image is partially correct, like this region seems to be fairly trustworthy and also seems very trustworthy here. But here, you just created an artificial grain boundary of your crystal by having an incorrect initial position. And like I said, these can be fairly subtle. And if you only look at the reconstructed object, you don't check your proposition, you may be missing this or misinterpreted all your Tycho reconstruction result. And yeah, so if you're doing strain measurement or structural analysis, just keep these things in mind. It's already 12, so I'm just gonna wrap this up real quick. And in terms about like these face value quantitatively, like I said, there are previous literature discussing along these lines, but the regularization strength matters a lot. Like if you have sparsity constraint, that will significantly change the background and the relative intensity between the atoms. If you want to do quantitative analysis on this, make sure you're doing things consistently. Like you probably cannot actually compare things wrong with different conditions. And if you're trying to identify different atomic numbers based on your reconstructed object, you need to be very careful about the reconstruction parameters and the regularization you are using. And this is another subtle example of the regularization strength that I recently figured out, maybe a couple months ago, that when I was using Tycho Shelf with the KZ regularization, I'm getting this incorrect contrast between the layers. So if you're familiar with 2D materials, you will know that they form hexagon shape. And this is a twisted bilayer 2D material. And in this Tycho Shelf reconstruction, you can actually see that Tycho Shelf missed misreconstructed the whole thing by having a hexagon all look brighter than the other one. That is just not physical because we actually have a transition metal dihydrogenide. So having an incorrect regularization strength can actually mess up your atomic contrast in a very subtle way. And we do have a simulated result shown in the Tyra paper supplementary. So just something to keep in mind as well, that even you have very nice looking images, they're all multi-slice reconstructed, you can still get very subtle artifact in your retrieve phase values. So here's just a summary: calibration, artifacts, and quantification. They're all critically important, and you want to do this very carefully. Lastly, just want to acknowledge a lot of these calibration work was done back in UIUC starting 2022 when we first got an MPAD trying to figure things out. And the rest of the regularization, the quantification stuff were mostly done in Cornell, in Muller Group, and just want to thank all the funding agency, and that is pretty much it. So lastly, just want to advertise a little bit about the TyRed, which is now enable up to 20, 30 times faster reconstruction comparing to Ptychography and Pi40 It's pretty accessible and flexible. You can do very nice typographic reconstructions as simple as just start using it by pip install TyRed. And that's the end of my talk. Thank you for your attention. I'm happy to take any questions.
Okay. Yeah, great. Thanks, Chia Hao, for a very nice presentation. I think your talk set a really nice tone for the rest of the study group. We actually have more speakers who will talk about other type of artifacts or optimal conditions for different electron ptychography applications. I actually need to go to my next meeting, so I'll let you to moderate the rest of the meeting. But before I go, I do have one quick question about your examples on different probe giving the same good object.
Oh, yeah, sure.
So I noticed you are doing multi-size ptychography, and the object you are showing is just the sum of all the layers, right? So if you look at the individual layers, do you see the differences from different probe reconstruction?
Good question. Not as much.
Okay, that's interesting.
So for these, you can see that this one's a slightly more blur here because this is literally a terrible probe. But along the depth, they seem more or less okay. And I think that's because all these probes in reciprocal space, they are all pretty much the same. They're more or less limited by the convergence angle there. And the reason we're seeing the real space probe being so messed up is mostly because the phase instability in the reciprocal probe phase.
I see.
Hi, I'm Xin. Actually, it's quite common in my reconstruction. I have many different data sets which have a good phase, which cannot determine by human eyes. And it has very, very bad probe shape.
Yeah. That's something we're actively working on recently. And I have some new feature I haven't get to release. But this seems to be a fundamental challenge in line ptychography with probe retrieval when you parameterize your probe in pixel space. Because when we do the gradient descent method, all pixels are freely, they can change freely independently from each other, which is okay in real space, but in reciprocal space, especially in your face, that's just not good because face needs to be fairly accurate and smooth before you do the wrapping. So anything checkerboard artifact in your face will just get you displaced probe.
I see. That's very interesting. I learned something new today. Okay, I really need to go. So Chia Hao, you can answer more questions.
Yep.
Okay, thank you again. Thanks everyone. Bye-bye.
Thank you. Bye-bye. Alrighty. Since we started a little bit later, so I'll stick around for maybe another 10 minutes. If you want to ask questions now, feel free to ask it. If you want to ask me later, you are free to use the Discord channel that we had the Tyra forum or the general forum or the Tyra GitHub issue, whatever form you prefer. The whole talk is already recorded. I'll be putting it on YouTube afterwards. So if you have another meeting you need to catch on, feel free to go. Thanks for coming on.
Hi, Jiahao. I do have a question about the if we have a small Kmax, then we have a large pixel size, dx, then it's limit our resolution.
Lateral resolution, yes.
Yeah, lateral resolution, yes. And if we have our diffraction space, then we decrease our dx. Then can we improve our spatial resolution?
Great question. And there are previous papers claiming that by padding your diffraction pattern, you can get better spatial resolution. I personally don't buy that argument because if you don't collect that, personally, I don't buy that argument just because if you don't collect that spatial information in your diffraction pattern, whatever you're reconstructing is only a guess by the model, and it's just not confined by the data itself. So you can probably say in this way, I reconstructed something looking incredibly sharp. Maybe let's say maybe this is a better example. So like I reconstructed something incredibly sharp. I can see spatial frequency up to this is like 10 picometer somewhere here, and even smaller up to here. But these spatial frequencies are not supported or are not provided by your data. So essentially, what you're saying is you are reporting or reconstructing something that's beyond your data, which to me, as a microscopist, I feel very skeptical about this thing. But padding can still help in the sense of, first of all, get you smoother real space representation by having a smaller pixel for sure. And for the parallel padding, it seems to stabilize the probe retrieval as well by having a smooth background that you're actually constraining it. So you'll see that in Tyred, the default padding method is actually not zero padding. Instead, we're using a parallel padding. But like I said, there's no actual data in the original diffraction pattern. So what we are doing is similarly adding information that wasn't there. So that's kind of why at the end of the day, you do want to bandwidth limit your reconstructed object so that you don't actually report anything that's beyond the range of your diffraction pattern.
Yeah, Jiahao, actually, I think this question can be translated to what determines your lateral spatial resolution in typography.
Yeah, and I think
I do believe definitely you collect more Kmax, then you have better spatial resolution, definitely. But is there a direct connection between the like Kmax transferred dx with your spatial resolution number?
I will think it this way. So if you have a perfect Tycho reconstruction, then in principle you will have your object, your probe, and your position all reconstructed correctly. Then your object will still be limited by the highest spatial frequency provided in your diffraction pattern. And you can actually try this by yourself, which is you take an atomic potential as a ground truth of your object, which is extremely sharp. You can have almost like a delta function in your object, and you just run through a diffraction pattern which you collected up to a certain Kmax. With certain number of iterations, you're gonna see the ground truth actually blur up to the spatial resolution that's matching whatever bandwidth limited spatial frequency at the end, because that's just the part that's fundamentally limited. And even you start from a atomic potential that has spatial frequency up to this point, at best you will be reconstructed up to this point, right? So up to whatever spatial frequency you have in your original objects. So yes, I do think there's a direct relation between the lateral resolution and the collected angle in your diffraction pattern, given enough signal-noise ratio in your dark field region. Of course, for low dose data set, you don't ever reach the Kmax you collected.
Thanks so much. And for the probe position artifact, actually I have many data sets. Can you to the position gap slide?
Oh, position guess.
Yeah. It's actually very common if your sample is an insulator. Then if there is a charging effect, then you have some position. You have a abrupt drift. Abrupt, not drift.
I
change
see.
of your
Oh,
scan position.
yeah.
Then you are very likely to have a gap after the iteration.
Oh, yeah.
And our kind of method is you can first clean your initial scan position, because you can kind of see the change of scan position in the virtual bright field image. And just change the initial guess.
Yeah, no problem. These scan position things very, very critical, and do highly recommend people to you either get a faster detector or to actually check out how to correct them beforehand. I'm hoping to add these features into Tiger sometime soon, but we'll see. Yeah.
Great. Thanks so much. Great talk.
Thanks.
Hey, Harry.
Yeah.
Hi. Thanks for the talk. Great as always. I had a quick question about your donuts versus the double cone.
Yes.
So how do they? I guess I understand the different origins of them physically, but when you're looking at them, like especially in projection, I would imagine they look very similar. Like this dark in the middle, and then this like kind of light like streak going out. How do you like know when you're getting which?
So personally, I think it's scientifically interesting to figure out which one's which, but practically I would say the donut thing. Most commonly, you will see this thing as a whole column. They're all donut all the way out. But for this double cone artifacts, for most of the data set, you don't actually see it because the slice thickness is much thicker. So when you have a 1 nanometer slice, you don't actually see these. You don't actually see these features because they're much weaker, and you usually get another atom very nearby. So you don't actually see this unless you're at the very top and bottom slices. So this is just a good example to show when you have single atoms, you do see these double cone artifacts. But practically, most people will probably see these donut atoms much more often when they have a dense material with heavy atoms, like bismuth, neodymium, like these heavy atoms. You usually see these all the time, even with very thin samples.
Okay, got it. That makes a lot of sense. So it's like
and this one you can remove it. This one, I don't think there's a optical method to remove it. There's probably only post-processing you can remove it, because I think this is fundamentally related to the missing wedge.
Just a lack of
the lack of information along the z direction. And these angles do matches the convergence angle of your collecting. So if you change the convergence angle of this, the angle actually changes as well.
Okay, cool. Thank you.
Yeah,
that makes sense.
Okay, so it's already 15 minutes past 12. I believe people might have other arrangement. If there's no further question, I may just end the Zoom talk here, and just reminding folks that next week we'll have Professor Yichao Zhang giving a talk on the multi-site electron ptychography application on resolving Moiré phasal that recently be accepted and published on Science. So I'm sure next week Yichao is going to bring us a very exciting talk. And like I said, this the whole core idea of TIRED is to build something that the entire community can be building on, so that everyone can start publishing better and more interpretable Tycho results. So feel free to just like ask your questions in the GitHub issue or in the TIRED forum inside the Discord channel. I'll try my best to answer the questions if I know the answer, or to come up with a discussion so everyone can move forward together. So since there's no further questions, I'm gonna end the Zoom talk here. So thank you all for coming. I hope you have a wonderful Friday and a nice weekend to come. I will see you next Friday. Bye.
Thank you, Chia Hao. Bye bye.